deep learning and deep learning we're organizing in our group. So thank you very much, Marina, for taking the time to do this. So Marina is a grad student working in the Applied project with John and me, and she's been doing great work on UP data. And she took the time to prepare some slides for you on CNNs applied to image analysis. So thank you very much.
Thanks. All right, welcome everybody. Thank you so much for joining. I'm going to talk a little bit about convolutional neural networks, which are used to analyze images. I'm mostly going to be talking about the basics of how they work, a couple of considerations when analyzing astronomical images, and then the final example that a new notebook, Jupyter notebook that I'll distribute to everyone is astronomy specific. So, and I'll also share some resources that I like for CNNs as well. So, nope, okay, that's fine. Just do it manual style. So a brief review. If you were here last time, Carlos gave a wonderful talk on the basics of neural networks. So essentially these it's a tool for finding a nonlinear mapping, right, between an input and an output. So you have these, a bunch of hidden layers of what are called neurons. They are laid out such that they are supposed to mimic the human way of thought, real human neurons. So we have an example here. So we have an input X, and these are our input layers, and we have a set of hidden layers of neurons that we'll call J. And each of these are connected to each other and weighted by a value that we'll call W, our weights. And the sum of these weighted inputs are operated on by an activation function. So this is what actually creates the nonlinearity in what we're doing. We'll call that F. And so A is our outputs, right? So we're weighting our inputs by this value W. We're trying to gain some information from our input, learn from that, and pass it along, and figure out the nonlinear function. So this is what a typical, what we call feed-forward neural network looks like. It means that your neurons from one layer are connected to the ones from the next layer, and so on, and the flow of information goes this way, right? There's no what we call back propagation. There's no learning from here that goes and circulates back. So this is useful for a lot of different tasks, but it's not particularly great for images, right? You're basically squashing all of the information of an image into a singular 1D vector. So you're losing spatial information from an image that could be very helpful in terms of learning more about it. So we need something else to help us do that. So this is where the field of computer vision comes in, right? How do we train computers to actually see images and learn from images? And that, just so that we're all on the same page, I wanted to do a brief overview of images, what they are. I'm sure most people here do more image processing than I do on a day-to-day basis, but just so we're on the same page. So a digital image is, you can just basically think of it as a 2D array of pixels that encode the appearance of a scene. So a scene is, for people who are able to visually see, that is what your eyes are seeing, right? The photons that you're picking up, these are your receptors, and this is what you're able to see. A camera, same thing. That's what you're able to see through the lens of a camera, telescope, anything else, a sensor that can pick up that light, right? So for an image, let's say of size, M rows, N columns, at each pixel at a location Mn, you're going to have an intensity value, right? This is a 2D intensity function, and usually that's between a value of 0 and 255. So for black and white grayscale images, typically that means lower values are going to be darker, higher values are going to be brighter, right? And so a value of 0 would be something like black, and 255 would be white. So this is what we see, right? But a computer needs something else. It can't process that the same way that we can. So if we zoom in on a set of pixels here, this is typically what a computer sees, and this is what it ends up learning from, right? These intensity values right here. That's what it can process and understand. And for color images, it's, instead of being mapped to a singular intensity value, you're mapped to an intensity for each color channel that you have for your image. So for this example, red, green, and blue, right? So you have a different intensity for each one. combined together gives you a picture like this that we're used to seeing. So it doesn't necessarily mean that they'll have the same intensity in each color channel. So the very first convolutional neural network, this thing that we're using to analyze these types of images, the very first one was introduced around 1979. It was basically a hierarchical neural network that was designed to look at handwritten Japanese characters, had its own training algorithm, and it's kind of essentially thought of as the first CNN. It was developed, well, it's still being developed to this day, but over the first decade in the 1980s, this was kind of the first CNN. It was actually pretty good at picking up visual patterns in images. But the real kind of change came with the introduction of this network called LINET from this team in 1998. And the big change here is that we are now introducing that back propagation that I was talking about, right? So you're learning from your image. You're updating your weights of your neurons. You've made a prediction, and based on that prediction, you're updating your weights further back in your neural network to see whether that was a good prediction or not, right? And you're iteratively learning based on these gradients. We're saying it's gradient-based learning. So this was kind of the first to introduce that. And it's grown very much since then. It's a very fast-growing field. So I'm going to talk about the main layers, the most important layers of a convolutional neural network. It's these three right here. So the convolutional layer, the pooling layer, and the fully connected layer. These are going to be the basics of our network. So starting with convolutional, the way that this works is you have an input image of some size. You select a filter or a kernel, which is a smaller representation or it's a smaller image basically that slides across the input image. And every time it does that, it's doing a convolution. It's computing a dot product between the two of them. It's matrix multiplication. It's two matrices and you're multiplying them together. And based on that, it's taking those input values, those intensity values, and creating some sort of output that's supposed to be learning features about your image, right? And we call that output a feature map, essentially. So this can be done for a variety of data. Like I said, you can have a 1D convolution where it's one less dimension and you're trying to learn from some data. Here we're doing 2D convolution, so we're learning from images, but you can also do it you can expand the dimension as well and do 3D convolution as well. So this is, videos, which are just sequences of images like this GIF, or an MRI scan. That's why they have to have you lay very, very still because it's building a volume of 2D image slices that are all aligned together, right? So you can do these for this type of data as well. And based on the color of your image, so you're performing this for each channel of your image. So for example, if you have a black and white image, you're only doing this for one channel. If you have an RGB image, you're doing it for 3 different color channels. You're performing this convolution 3 separate times in a depth of 3. And as Dr. Angeludi mentioned yesterday in her defense, this is why we want to normalize our data because we are trying to learn from the pixel values. And so we want them to be in consistent ranges across our data, both the training data that we're using and any new data that we're introducing to our network. We want it to be consistent so that it's easier for the network to process these and learn from the images, right? Say you have a network and you trained on really bright, colorful, images of dogs and cats. If you introduce a bunch of very, very dark images and only black and white, it's probably not going to learn super well from those, right? So if you haven't normalized it, it's not going to learn as well. So there are a couple of really important parameters that we need to think about when we're doing our convolution. So the first is the size of our kernel that's learning. Typically you have sizes like 1 by 1, 3 by 3, 5 by 5. You typically use odd numbers because they work out geometrically a little bit better. And your kernel position, each time you're done doing a convolution, is shifted by a certain value, and we call that stride. So this is an example on the right of a 4 by 4 input image, and then you have a 2 by 2 kernel, and it's going across 1 by 1 by 1 column, right? So that's a stride of 1. Whereas on the right-hand side, we have a 5x5 image and a 2x2 kernel, but it's going across every other, right? It's going two columns at a time, so that would be a stride of two. Um, Additionally, we can have something that's called padding. That's where we are adding extra, like a border to the border of our kernel. So an extra border. Typically, it's a value of 0, so you're not adding more intensity values to it. It's just a 0 border around it. And that helps maintain the size of the resulting convolved image. And it also helps because generally when you perform convolutions on an image, your edge pixels, the pixels out here typically receive less convolutions than the pixels in the central region of your image. So this helps expand it outward a little bit. So it makes sure that the edge pixels receive more convolution. So you're looking more at the whole image versus the other way around. So you can calculate the padding, the size of that based on your filter size, essentially. So your filter size -1 divided by 2. So you can also consider something that's called dilation. It's essentially increasing the receptive field, which is this right here, the shadowed portion on your image from your kernel, affecting the filter's output. And the most likely reason that you would want to do this is because you want to capture more contextual information about your image. You want a larger area to cover. So let's say there's a feature in your image that is not perfectly captured within the receptive field of the kernel that you're using. You want to go a little bit outwards. Then you could use dilation and say, hey, I want to go every other pixel so I can encapsulate all of that at the same time. I would say it's not as common to use this, but it is helpful. Like I said, if you have a feature that's not typically captured in a typical kernel size. And finally, we have our activation function. Carlos was talking about last time that we typically use the rectified linear unit for images. This is what's adding the nonlinearity to your network, right? So the reason that ReLU is typically used is because it's replacing all your negative values with 0, which is what we want for intensity, right? Usually between 0 and 1, or normalizing it between the minimum and maximum, things like that. We want it to be above 0. So that's what that looks like here. This is essentially just replacing all the negative numbers with 0 and keeping everything as positive. All right, so you can essentially calculate what your output size, your convolved image is going to look like based on this. So it's just a function of your input size, the filter size that you choose to use, your dilation, which I said usually that's 1 if you're not wanting to expand it outwards, and then your padding and your stride. So for example, if I have a 5x5 image, here this example is using values of 0 and 1, but in real life, obviously you can have values that are higher than that. So for a 5x5 image, I've selected a 3x3 kernel. You see it's moving 1 column at a time, so my stride is 1. And then this is my convolved feature that it's doing right here. So if I have 5, 3, so that's 2, I'm using a normal dilation, so that just knocks that out. And then I'm not using any padding, so that knocks that out. So it's essentially 3 plus, how big was it? 5x5? Yeah. So that means I'm going to have a 3x3 image, right? A convolved image here. And so I'm going to talk a little bit more about how you get these values right here. So you can perform something that's called pooling. And that's basically where you're progressively downsampling or reducing the spatial size of the output feature maps while retaining the most important information about your image. And this is good because it decreases the number of parameters that your network has to learn. So it takes less time to learn, less compute time, and there's less of a likelihood that you're going to be overfitting your data, which we're going to talk about more in a minute. So there are a couple different ways that people do this. The most popular ones are maximum and average pooling. So essentially that's just what it sounds like, right? For maximum, you're taking the highest value from the area that's covered by your kernel and keeping that value. Your average pooling, you're taking the average value of the area and keeping that. You can also have some other kinds, minimum pooling, sum pooling, again, just like what it sounds like. Those aren't quite as popular. These are typically used because a higher value is going to mean that there's a higher likelihood that you've learned a feature from your image, while a lower value is going to be the absence of a feature, right? So this is, like I said, this is helpful in reducing the spatial size of your image as you're going along. This is a good example, in my opinion, about how that differs between an input image and how the two main ones, how the convolved image looks like after that. So, if you have a black and white one, use max pooling, it's not picking up that feature, where you're taking the average here. This one keeps the feature the same, takes the average here. And finally, we have what are called our fully connected or dense layers. So these are the final layers of our network, where we're typically right before this, we have flattened our data into a smaller feature vector for the network to understand. And this is the layer that connects all of the neurons to the previous layer and is typically, if you're doing a classification task, this is the layer that's going to be responsible for actually classifying the image into certain outputs. So it's producing the final output where usually your vector is a score of classes, class scores, and you're trying to decide which it belongs to. What is the output of that? So typically in a basic architecture, as part of your feature extraction for your images, there are multiple iterations of these convolutional blocks. Like I mentioned, convolution, activation function, and pooling. You have many of these. And then at the very end, you have your fully connected layers that give your output. So this is very much an iterative process, right? Your convolutional blocks are going to learn different things about your images as you go along. So when you first start off, you're probably going to learn more like broad features, edges of your features. You're going to learn maybe corners, and then it gets more abstract and more complex as you go to the convolutional layers beyond, textures, things that are really hard to pick up, really hard to find patterns. So you want to design it so that it's accurately picking up those things as you go along. So what do these output feature maps actually look like? I think this is a very fun thing to look at because I'm a visual learner and I like to see what the network is actually learning. So this is an example that I made with a personal photo I took in the moon a couple years ago. So this was a black and white photo originally. So you can see some of the layers at the top. They're learning more of the whole object, right? They're the edges of the moon. And then as we progress to these layers lower down, it's starting to learn some textures on the moon surface, right? Some more weird edges, things like that. Things that are a little bit harder to pick up by the human eye, right? I also did one with my roommate's cat that I thought was pretty cool. So this is a color image originally. But same type of thing, right? Edges. Sometimes it doesn't even look like anything at all. It's just looking at the contrast, the brightness, and then looking at more minute features here. So this is used with a tool called GradCam. There are several different tools for looking at feature maps like this, but I really like this one because it's really easy to understand. So now we have our network set up, right? So how do we make a CNN generalize well on new images that we introduce to it? So there are a couple things to consider. So we want to find a good balance when we're learning with the data that we're introducing. We obviously we don't want it to not learn at all from our data points, right? But we also don't want it to do what's called overfitting, where it's catering exactly to your image set, but if you introduce anything new to it, it's not going to learn anything from that, right? Because it's too catered to your training. So we want to find a good balance of the two. And there are a couple ways that we can do that. So one of the things that we can do are called data augmentation. So those are things that you can do to your input data that you're feeding to your network. These are just, typical, things you could do in Photoshop. I mean, you're cropping them, you're rotating them, because you're going to see different images in the real world, right? Rarely are you going to see everything that's perfectly straight on every single time. You know, they're going to be a little bit noisier. They're going to have different resolutions, right? So you want the network to learn those things and prepare for those things, right? You want it to be invariant to those different types of changes in your data. Adding noise is one of the biggest ones, right, in astronomy. And different colors, right? You're not gonna have the same color, same brightness, same contrast of every single image. Perfect example is, like I said, astronomical images. When are you ever going to see a galaxy the same shape, the same angle every single time? That would totally negate the paper that I'm about to publish. So you want to make sure that's invariant to the rotations that you're seeing in these images. And so you can basically do that before you train. You just feed it, and it gives you a bunch more data to train the network off of, right? So if you don't have a lot of images to begin with, this is a way that you can build up your training data volume. Okay. Some other things that are typically helpful, and this is not just specific to images as well. We call these regularizations. So this is essentially changing the weights that you're learning for each of these neurons, right? So some popular ones are called L1 and L2 regularization. So you're essentially introducing a penalty term to the loss function that you're interested in. So typically like a loss function for CNN. So for this example, for L1, it's proportional to the absolute value of your weights. So essentially, you're encouraging some sparsity. Some of those weights go to 0 completely. And then for L2, that's going to be the proportional to the square of your weights, right? So that's actually reducing some larger weights, so everything's a bit more smooth. Your model's smoother when you're training. And the last one is full dropout. So essentially, you're deciding on a fraction where a certain number of neurons are going to randomly not be considered. Their weights are not going to be considered. So for example, let's say you have a network that's looking at some images and it's just really particularly concentrated on this one feature. And you want it to consider something else, you want it to have more context, but it's just really considering this feature only. Well, you can use something like this so that the weights are not so focused on that feature and they can randomly be dropped out. So there's a bit more, there's less dependency on those particular weights for that part of the image, right? So you can drop some of them out randomly. Okay, but classification is not the only thing we can do with CNNs, right? So there are a lot of different tasks that we can do. So image classification is just a task of object recognition, but you can also find the object where it's located in an image, right? And when you combine those two, that's what's known as object detection. And we can also perform something called image segmentation, which is more to do with the pixel values of our image. And I'll show an example of that in a second. So for classification, this is the main task that we were talking about. But what if I want to know about exactly where that class is located in the object? Then I have to have some sort of localization. I'm finding a box in where that's located within the image that class is located. In object detection, I'm doing both of those at the same time. So I'm finding where the object is located, and then I'm also classifying what the object is, right? For instance segmentation, I'm interested in the individual instances of that object showing up in the image. So instead of just cat, dog, I'm interested in cat 1, cat 2, dog, dog. So the individual occurrences of those objects popping up in the image, right? In addition to where they're located in the pixels. Another example would, oh, no, there we go. So in terms of the difference between instance and semantic segmentation, this is going to be where you're not as concerned about the instances, right? You're just focusing on the pixels themselves. So all I care about is that pixel is associated with the sky, that pixel is associated with cat. I'm not caring about where it's located in the image, right? I'm classifying just the pixels. Whereas this one, like I said, this is for individual instances. So this is dog 1, dog 2, cat, and I know exactly where they're located in the image. Does that make sense so far? Okay. And like I said, this is the same thing I know exactly where this object is within my image and I'm classifying it. I know exactly where multiple objects are in my image and I'm classifying them. So if you're like me and you've failed a Google image captcha verification 3 to 4 times and are ready to throw your phone against the wall because you know what a street light looks like, but apparently Google thinks you don't. You have to remember that you have to think about it not like a logical human, which is the whole point of the task in the first place, but you have to think about it like a computer, right? You have to start thinking about it. Okay, how many pixels in this part of the image belong to a crosswalk, right? And I swear the more that you do that, the easier it will be to, to solve those on the first try, because that's exactly what it's doing. It's doing these tasks right here. It's saying, where is this located in this part of the image? Okay. So the start of the revolution of CNNs was around 2010 when this imaging data set was introduced. It was not this many images when it first started, but it was introduced by this team as a challenge to others. It was a diverse set of images, animals, nature, different things. And they were challenging people to build CNN architectures that could perform well on this diverse data set, right? And it's called ImageNet. So since then, there have been a lot of really great architectures that have been built. I mentioned the very first one in 1998, but these are some of the winners of that challenge over the years. They're good at doing different tasks. Like I mentioned, classification, object localization. This is not a comprehensive list. This is just some of the well-known names that we have. So why do we care about these? Why? I mean, good for them. That's great. They won some awards, right? But the important part is that they're very good at doing what they need to do. And we can actually use that for our own benefit. So we can do something that's called transfer learning. So these architectures have already been trained, right, on this ImageNet data set and other data sets. We can actually use those weights. Those have been stored along with that model. And you can typically access them fairly easily through different machine learning frameworks. And you can actually use those weights that have already been pre-trained and use them as a starting point for your own tasks, including, astronomy images, because they're really good at extracting features. That's what they were designed to do, right? So they can oftentimes find more patterns, more features in your data than if you just handcrafted them from the very beginning, which is great. And they have improved performance and they help reduce that overfitting that I talked about. And they've been designed to be applicable to a bunch of different types of images, right? And they have a lot of community contributions. People have been working on this for a really, really long time. So there are a lot of different tutorials, examples of how you can use this for your benefit for your own data set. Okay, so it's time for an astronomy example. So I was trying to make my own really nice galaxy classification notebook, but unfortunately, memory is typically your worst enemy when you're doing CNNs, and that's what I was running into, memory issues. So I decided to go with someone else's because it's really good. Let's see. So I will share this with everyone. It's on Google Colab. You can also upload it to Kaggle, so you can use not your own computer. You can use an instance of something else if you don't want to run it on your own computer. So I like this one in particular because uh, it does what I just talked about. So it starts off with just crafting your own neural network from the beginning, something really simple to analyze images. And then it also loads some of those pre-trained models that I talked about to see how they compare in terms of performance. So this particular data set is some near-Earth objects that were observed at Cerro over 5 nights. And they are trying to essentially determine if the image has a point source in it. So one of these objects in it into the co-added images. So this is what the images look like. So these are examples of, yes, these are true positive. There is a source in there. And this is an example of things that were classified as having a source in there, but do not actually have them in there. So you can download this data set of near Earth objects, and like I say, you can modify this to a framework of your liking if you have some experience doing it in a certain one. But it's very, very straightforward. It has a very, very simple model, like I talked about. It just has for this example, it just has one. It has two fully connected. You don't even use any convolutional layers, right? You can just see what it thinks without doing any convolution, any feature extraction. And then as we go through, you can add convolutional layers to it to see if it gets any better. This is what we typically look at for a classification task. We see, okay, what is the percentage of images that were accurately classified as what they're supposed to be and how many were not. So theoretically, if all the true images match the labels of the true images match the labels of the predicted images, then we would have a straight diagonal of 1, which is what we want. You can also see, I pop up there. You can also see how the model is learning as it's going along. So this is, in this case, we're trying to minimize a loss function. So we have a training loss, and we also have a validation loss where as it's iteratively going through, it's checking on some new unseen data to see if it's actually generalizing on that. So like I talked about the overfitting, that usually looks like either you're doing really, really well in your training accuracy, you're learning, right? But actually your validation accuracy is either, plateauing or it's going down. There's a huge gap in between the two, which means you're still not actually learning on new unseen data. So you can track that as well. And here I mentioned you can download this and use a little bit more of a complex network, a deeper network. And I like this because I mentioned you can use these well-known architectures as a starting point, but you can also modify those too. So you can add more regularization to it if you wanted, like an extra dropout layer or something, right? So they're meant to be a starting point. You can modify them further. So yeah, I think it's a really good example of how to make small changes to see how it improves your performance. And I will share this with everyone. Yes. That is about all I had in terms of an example. I'm happy to answer any questions about CNN, the architectures or anything else. Thanks. Yes.
This context in the campus in the building. So usually we have several channels first with the core. How the CNN combines the core information, because what I have seen is the only part where there's the core information for paintings or whatever core information. It's done when you go to the dense measure, where it's all of these things around.
Yeah, so you specify that at the very beginning. So maybe I can show an example of the one I was trying to do. Yeah, you want to specify it at the beginning because you are performing the convolution per channel. So typically you specify, so for instance, I was going to use images with 3 color channels, so RGB. So I'm specifying that I'm doing a 2D convolution on an image, right? But my input shape is going to be 32 by 32, and then the depth is 3 because I want it to do it across 3 color channels. So typically you specify that at the very beginning and then do the same process all throughout. So it's performing that for each color channel that's in your image. So if I just wanted to do it on a black and white image, then it would be 1, right? So this is the depth of your image set you're performing all of this for.
combines the former information and moves in the convolution.
Yeah, so when it performs all of this per color channel, and then when you get to the very end, you're combining it into a singular featured vector, right? You're combining it to one vector and then performing the classification. So that's where it all comes together. And then Mhm.
How no one is going to be learning that if internally it's not combined for chance.
You're saying if you only want to learn from two color channels versus all three.
Oh,
Mhm. Oh, you mean in terms of like the value, the astronomical value of a color,
Yeah.
right? So in that case, you would want to use something else that this is going to be purely for the image itself. So if you can, there are definitely multimodal abilities that plenty of people here have worked on, where you can combine images with other information about the image, like a spectra. You can combine other single values about the image, but you have to have something that's a bit more complex. So you have to have something that can take both images and other, text values, spectra, other things, and then assess those at the same time. So this would not be able to do that in terms of taking in other values in terms of like astronomical color. It's just assessing the color of the image that you're inputting for it. That makes sense. So there might be features that are the image has that you don't even realize that it's picking up on. And those could be included in your convolutional layers that it's learning. But if there's something you explicitly want it to learn from, then you have to have something that also combines some other, text value, like I said, that can do that as well. It is possible, yeah. Just a little more complex. Okay.